Welcome to this 12th lecture on calculus of variations. Okay, in this lecture what we will do is we will try to look at a generalization of Euler's equation. In the last videos we have derived this Euler's equation, and in this current lecture we will try to have a generalization of Euler's equation that is called Ostrogradsky equation. I'm sorry. So this is where we are heading. Let me just change the color. We are trying to find this generalization of Euler's equation. So let's see what is this generalization. In case of Euler's equation, what we had this functional fxy y dash dx. This was our functional. So here we had this input function as y of x, and y was a function of x only, one variable only. So the domain here was set of functions of one variable. Okay, in case of Euler's equation, we had these functions of one variables in our domain, which we are using, like from where we are taking these y's for this defined functional, right? But so it means that so far we had considered functionals depending on functions of one variables, and function of one variables are curves, right? So now, but in many problems, we can encounter situations like this: f x y z z x z y. Okay, so basically we have this z as our function, which is our input to this functional f. Okay, and these x and y are the independent variables. So it means that z is actually a function of x and y. Okay, so now we are trying to look at the case when the input function which we are giving to our functional is a function of two variables or more than one variables, we can say. Okay, so for keeping the notation simple, we will confine ourselves to the function of two variables only, but you can obviously apply these things when there are n number of variables. Okay, so what I'll do is you will consider a function f which is a function of x, y, z, p and q. This p stands for partial derivative of z with respect to x, and this q stands for partial derivative of z with respect to y, and this z is a function of x and y. Okay, we have this function capital F. This function is such that it has first order and second order partial derivatives with respect to all its arguments, with respect to x, y, z, p and q. The second order and first order partial derivatives should be continuous. This is our assumption that our function f is such that. Then we try to look at this functional. We have this functional where we are making our input as z. Okay, z is the input to the functional, and it is further a function of two variables. Okay, and we have this j of z is equal to integral over some closed region in R2 space. Okay, f x y z z x z y dx dy. This is our functional. You must be knowing that this is the functional we consider in case of Euler's equation. Okay, so correspondingly this is the functional we are considering now, right? This is a functional, and what we are trying to find is we are trying to find a function z of x y. We are trying to find z such that first and second order partial derivatives of z are continuous. Okay, then z satisfies a given boundary condition. So you have this region, closed region R, and this is the boundary of that region. Let's call that boundary as tau. Okay, this is the boundary of the region. This is gamma. I'm sorry, this is gamma, and we assume that this z is having a fixed value. Z at gamma is specified. Z at this capital gamma is specified, pre-specified. Okay, so we are looking for z with first and second order partial derivatives continuous. Z takes a given value on the boundary gamma of R, and for this particular value of Z, this functional J of Z has an extreme value. So we are looking for the extreme value of this functional such that it is uh, specified on the boundary of this domain R. Okay, so this is basically a fixed boundary thing. We are looking for this extreme value of this functional where the value of the functional value of the functions, this Z value of the admissible functions is specified at the boundary. So basically these two conditions are the required conditions for our admissible set. Okay, admissible set. We have talked about this admissible set again and again in the previous videos. So basically admissible set means the set from where you will take your input functions, right? So these are the two conditions which should be satisfied by your input conditions. So I think it is clear now that what we are trying to do. Let's do it. Okay. Okay. So as before, how we will derive the necessary condition. Necessary condition was that the variation should be equal to 0. The variation of the functional should be equal to 0. Okay, so this condition will has already given us the Euler's equation in the first case. Okay, Euler's equation in the first case, and if now we will try to impose this condition, we will get the Ostrogradsky equations. Okay, in this particular case, for the function of one variables we got the Euler's equation, and for this function of two variables or more than one variable we'll get this Ostrogradsky's equation when we apply this condition that variation of the functional should be 0. We already know that why this is a necessary condition for the extreme value of the functional. Okay, so we need a lemma. We already had this lemma, similar kind of lemma, but we will specify it again to be more specific. Okay, so before deriving this equation, we need this lemma. Let us see what is this lemma. This lemma says that suppose you have some alpha. Let me just change the color. You have some alpha xy. This is a fixed function of two variables. Okay, and it is continuous in the region R. You have this xy plane. Okay, and this is your region R, closed region R. Closed means that every point is an interior point, and this is the boundary gamma of R. Okay, so and you have a function alpha xy defined on this R which is continuous. Okay, you have this function alpha xy which is defined on this region R and it is continuous. And then if this integral alpha times h dx dy over this region R vanishes for every function vanishes for every function hxy. Alpha is fixed, alpha is one fixed function, and this integral vanishes for every hxy which satisfies some conditions. What are those conditions? The first condition is that this hxy should have first and second order partial derivatives continuous in R. Okay, so it means that partial derivative of h with respect to x, partial derivative of h with respect to y, partial derivative of h with respect to x 2 times hxy, hyy. All these five things should be continuous in R. This is the first condition. And second condition is that hxy should be 0 at the boundary. If this integral is equal to 0 for all hx which satisfy these two conditions. First is that all these five derivatives should be continuous, and second is h is equal to 0 on gamma. Okay, then we claim that actually this function alpha xy has to be 0. Okay, you can try to remember that similar lemma we had derived before deriving this Euler's equation. Okay, let's prove this lemma. Okay, Okay, as before, we will prove this lemma by contradiction. What we want to prove that prove is that we want to prove that alpha xy is equal to 0 for all points in R. Okay, so suppose this is not true, and suppose alpha xy is not equal to 0 at some point in R. Okay, and call that point as x naught y naught. Suppose this is the point x naught, this is your R, this region is your R, and suppose there is this point x naught y naught where your function alpha xy is not equal to 0. If it is not equal to 0, it will be either positive or negative. You can assume anything. I am assuming that this is positive at this point alpha x naught y naught. Okay, now you are given that alpha xy is continuous, okay, in R, and also R is closed. If R is closed, then it means that this point x naught y naught is an interior point. Okay, so it means that you can find a neighborhood of this point x naught y naught inside this R. Okay, and alpha xy is continuous at x naught y naught. Okay, so it means that okay, alpha xy is continuous at x naught y naught, and alpha at this point x naught y naught is positive, you are assuming. Okay, it means that it cannot suddenly become 0 or negative. So it means that there exists at least a neighborhood around this point x naught y naught in which your function alpha xy is positive. Okay, this is from the continuity of the function alpha xy. So it means that there is a circle. Let us call that circle like this. It means that you are choosing that radius epsilon. There is a circle which is completely contained in R in which your function alpha xy is positive. Okay, is that thing clear? This thing comes from the continuity of the function alpha xy and the closeness of this region R. Okay. Now you choose a function hxy. How you are choosing this function? You are taking this function is equal to this thing, x minus x naught square plus y minus y naught square minus epsilon square whole cube inside the circle. In this circle, this function takes this value, and outside this circle it is 0. Everywhere else it is 0. Okay. You can check that this function is 0 on the boundary. This is the boundary. This is the boundary. Okay. And this circle is completely inside R. So this boundary is away from this circle, and this is how, and we have defined that our function hxy is 0 outside the circle. So it means that hxy is 0 on tau on boundary on sorry gamma on, that is on boundary. That is the first condition. And second condition, you can check that it is a continuous function and all the derivatives hx, hy, hxx, hxy, hyy, these are all derivatives are continuous in R. Okay, this you can check. So it means that this function hxy satisfies all the conditions of lemma. It satisfies all the conditions of lemma. Okay. So it means that by lemma we must have alpha xy, hxy, dx, dy over the region R should be 0 by lemma. We must have this condition, right? But you try to find this integral, what you will get, because you have this hxy 0 outside this circle. So let us call this circle as C, this small circle. So your integral will reduce from R to only C. So your integral is equal to integral of alpha xy, hxy, dx, dy, and this alpha xy is greater than 0 in this C, and this hxy is less than 0 in C, whole C. So it means that this integral is not equal to 0. So we reach at a contradiction. So it means that our assumption is wrong, and alpha xy is equal to 0 on R. Okay, this is a lemma. We need this lemma to derive this Ostrogradsky equation. Okay, let's do that in next slide. Okay. Okay. So we know how to do these things now. first of all we need to compute this variation delta j. Okay, so how you compute the variation? You will consider an admissible function. This is our admissible function. It means that it is fixed on the boundary. Okay, admissible function means we have seen that there were two conditions, that first and second order partial derivatives are continuous. This is the first condition for the function zxy to be admissible, and the second condition is it should be zero, not zero, it should be fixed on the boundary of the region R. Okay, so now let hxy be the increment. It means that this function, you are using it as an input to your functional, so it means that this function should also come from your admissible set. So this will come from your admissible set only if, number one, your hx, hy, hxx, hxy, hyy exists and continuous. Number two, h should be 0 on boundary, because if h is 0, then only this whole function will satisfy a given function, a given condition, given value. It will assume a given value on the boundary only if this hxy is 0. So these are the two conditions which hxy has to satisfy in order to use this function, this whole function, as your input to your functional. Okay, right. So you can note that these are the conditions of last lemma. You can see how everything is falling into place, right, so nicely. These are the conditions of last lemma. Why we assumed this condition for our admissible set. Now you can see why we assume this first condition for our admissible set. Okay, so that we can impose those conditions on h, and then we can use that lemma, right, to derive the required equation. Okay, now let us look at the increment. Increment in j will be j computed at z plus h minus j computed at z. So that will be fxy z plus h. It was zx, so it will be zx is partial hx is partial derivative of h with respect to x. Then zy hy, and this is from here, and this is from the second term. Now you can just uh, use the Taylor's expansion. This is Taylor's expansion. Okay, so what you'll get, it will be, for this, use the Taylor's expansion for three variables. So you'll get f x y z z x z y plus h times partial derivative of f with respect to z, then hx times partial derivative of f with respect to zx, then hy times partial derivative of f with respect to zy plus higher order terms. Okay, minus this f x y z z x z y. This term and this term will cancel. You will left with these three terms. Okay, fzh plus hx times fzx plus hy times fzy dx dy plus higher order terms. These are the terms which are having order greater than 1 relative to hx hy. Okay, now you compare it with this is the principal part of your increment, and this is called the variation. You can see this is something like this: del j is equal to delta of j plus epsilon into h. Okay, where this epsilon goes to 0 as h goes to 0, because this term at least contains second power of h. Okay, so you can write it like h into something which contains h. All the terms contain h. So this is your epsilon. Okay, something is your epsilon. So you can compare it with your definition of variation, and you will get that this is your variation. Okay. Now the necessary condition is that this variation should be 0, right, on the extreme functions, right. Let us see what is the equation we'll get. Okay, so we obtain our variation like this in the last slide, right. Now just consider this second part, last two terms. What is this? This is f(z(x) hx plus f(z(y) hy dx dy, right? This is a simple manipulation. I can write this thing as partial derivative of f(z(x) times h plus with respect to x plus partial derivative of f(z(y) h with respect to y minus these things. You can see here I can apply the product rule. I'll get f(z(x) hx plus h times f partial derivative of f(z(x) with respect to x. So this term will cancel from this term with this term, and similarly here. So I can actually write this integral as sum of these two integrals, right? Okay. Now there is something called Green's theorem. What is this theorem? This theorem says that the surface integral of this partial derivative of q with respect to x minus partial derivative of p with respect to y is same as the line integral of p dx plus q dy on the boundary, okay, along the boundary. So if we apply the Green's theorem on this first integral, okay, here I want to apply Green's theorem. This is your q, this is your q, and compare it with this, okay, and you need a negative sign here. So your p is actually minus fzy h. So this is your p, this is your q, right? So apply the Green's theorem on the first integral, you'll get this p dx plus q dy on the boundary, okay, minus this second integral as it is, right? Now because h vanishes at the boundary, therefore this integral vanishes, this integral vanishes because h is 0 on boundary, right? So you are left only with this second part. So you have this, this is only this delta j was fzh plus this, we were considering these two terms, na? So we have to finally include the first term as well. So you have your variation is equal to fz minus curly by curly x of fzx minus curly by curly y of fzy times h dx dy. Here h is the function which satisfies two conditions of the lemma. So basically you are saying that this integral is equal to 0 because this is our necessary condition that delta j should be 0 for all hx which hxy which satisfy the two conditions of lemma. Therefore lemma says that this function, this is alpha xy, should be 0. So we get that fz minus curly by curly x fzx minus curly by curly y fzy is equal to 0. This is the famous Ostrogradsky equation. Okay. In the next video, we will look at the examples of this generalization of Euler's equation. Thank you.